right, our next speaker is Petra Berenbrink, who will talk to us about balls and bins and the infinite process with deletion.
Yeah, thank you. Well, I did change the talk, so the announcement promised a slightly different talk, but I think balls into bins fits much better into a memory workshop. So what I'm studying here is an infinite balls into bins process. So meaning we allocate balls in bins continuously, and we have a probability to insert and to delete a ball. So I give you an infinite sequence. Beta t is a probability to insert a ball, and 1 minus beta t is a probability to delete a ball in a certain step. In my definition, I always use m of t as the number of balls in the system at step t. And whenever I use m in my results, then m is the overall maximum number of balls that were ever in the system at any point of time. And the goal that we have is to minimize the discrepancy, and the discrepancy is defined as the difference between the minimum and the average load. So not between the maximum and the average load, not difference between maximum and minimum, because in balls into bins we know that kind of the lower gap is larger than the upper gap. So it's maximum minus average load. So there are different models out there for this infinite model. The one that I basically said, let's maybe call it, yeah?
Is the discrepancy for a point in time, or is it the max overall time up to?
No, the discrepancy at a point of time.
Okay, thanks.
So there are several models that were studied. For example, the one that I just introduced, where we randomly decide between insertion and deletion. Then there is that reinsertion model. Here I have balls, and if I delete a ball, I could possibly re-enter the ball into the system, but then the ball has to use the same random choices. So that's not the model we are studying here. And there's also an adversary model, and here the adversary determines if in a certain step a ball is deleted or inserted. Now, a couple of results. Well, there's a very well-known result. I think one of the authors might even be here. And these guys basically looked at the balls into bins process with insertions and deletions, but the number of balls equaled the number of bins. Then there are other results. For example, the one by Berthold Föcking, he basically allocated sequentially n balls into n bins, but he also has an extension in his paper where he basically said that if I have m balls in the system, then the maximum load is log n plus O of m divided by n, which is of course relatively bad bound, because if m is large enough, that's even worse than the single choice protocol. So our work was basically motivated from the Fox paper a couple of years ago. There the people looked at the heavily loaded case, so you insert and delete balls, and they basically looked at the case where an adversary determines the insertion and the deletion. And the result of that paper shows that there is a huge gap. So if an adversary determines when a ball is inserted and when deleted, we have a huge gap. And the lower bound was even valid for 4 bins only. So they also looked at another strategy, which they called modulated greedy, and that strategy basically has to know the maximum number of bins in the system ever, and then it's a nice allocation scheme, but they do kind of need global knowledge, and then they get a bounds m over n plus order of log m for adversary insertions. So, and our goal was basically in this work to see what happens if not an adversary determines the insertions, but everything is completely randomized. So, and our results are the following. So we show several results, and if I basically say that the value x is bounded away from 0 or 1, I mean it's larger or equal 0 plus theta of 1. I mean, I think it's pretty clear. Huh? So what we show are several results, and the way that I present them, not every result might be very interesting, but it also kind of follows the proof that we do in our paper. So our first result is, let's assume the beta of t are bounded away from 0. Then at any point of time, the discrepancy is order of log n. And the number of balls above the average is linear in n. So we can also show that the bound is tight, and it is tight in the sense that if the insertion probability is a little bit too large, it is the insertion probability is 1/2 minus epsilon during a certain time interval, then the maximum load pops up to log n. So meaning without further restriction, this bound is more or less tight. So what we then did is we looked at the following. We assumed that at a certain time t, the load is perfectly balanced. And if the load is perfectly balanced, then we showed that for a polynomial number of time steps, we are able to have a maximum load or a discrepancy of log n plus a constant. And this holds as long as the insertion probabilities during that time are bounded away from 0 and 1. Then we show that additionally, if I give you a time interval of polynomial length, and during that time interval the load slightly, a tiny little bit increased, then we can show that the discrepancy at an arbitrary point of time, at an end of such a time interval, is log n plus a constant. So meaning if your insertion probability is high enough compared to your deletion probability, then you get a discrepancy of log n at every point of time. And to compare these two results, the first result, here I basically said that the discrepancy, the maximum minus m over n is in log n. And m in that case is the overall maximum ever. Okay, and in the second time, I look at the discrepancy, and the discrepancy is the load at that point of time and the average at that point of time. So there's a difference between these two results. Okay. So the first one is more the way that most of the results were stated, where we use the maximum load ever, and the second result basically says that if the time interval was kind of good, we call it C good, then you know that the maximum load is only log. Yeah?
So in the first of those, I relaxed it to be 1 plus epsilon times log n for a fixed epsilon. Does that increase the degree of the polynomial that you can achieve in terms of for how many steps?
The degree of the polynomial depends on several things. It depends on epsilon, but it also depends on the constant. So if you want to have a larger polynomial, then the constant, this order of 1 term, would increase.
But I guess phrase it another way.
Yeah.
What are the benefits if I wanted to, for a fixed epsilon, say that the difference should be at most 1 plus epsilon times log n? Because at least as I'm reading there, you're saying that the constant there is 1. And part of the log n, and I'm saying that if instead we're willing to, for a fixed epsilon, allow the difference to be 1 plus epsilon times log n, how would the results become?
I have to think about it. What would that mean? I think you could show something like that, but it's not pretty. But I think that should be doable. Okay? So, and so basically these are the results. So our final result shows that the above two results hold at an arbitrary time, as long as these conditions that in a long time interval the maximum load is slightly increased. So we have slightly more insertions than deletions. If that is fulfilled, that all holds at an arbitrary step of time. Now, the way that I structured the results is also a little bit the way that we've proven them, because what I'm doing next is, goodness, here is the definition of goodness, but I think what it kind of means, if I give you a time interval which is long enough, it doesn't contain shorter time intervals of polynomial lengths, so that during that time interval there was a heavy load decrease. So during that time interval there were much more deletions than insertions. Because, we need kind of some insertions to rebalance the system. So now, how do we analyze that? first, what we've basically shown is using a well-known potential function analysis by Perez, Talva, and Vida. They have a couple of papers where they use a very nice potential function, and the potential function can be used to show that the expected load of such a dynamic system at every time the expected load is linear in n. So that was the first time that we have shown. So basically what we had to do is they looked at the system only with insertions, and we had to take the potential function analysis and generalize it to insertions and deletions. But that's quite doable, that's not a big deal. Then we took an idea of Thomas Sauerwald that he showed in a paper, and what he basically did is, also for a system without deletions, he basically took the potential function, showed that the expected number of bolts above the average is linear, and he used kind of the same potential function again, and he showed that result also holds with high probability. So meaning if you do that, if you kind of combine the two results and generalize them to deletions, you basically get that with high probability, the number of bolts above the average is linear. And since that is an exponential potential function, you automatically get that the difference between the minimum and the maximum load is logarithmic. So that part was relatively easy. And then our idea was basically, okay, if you know that with high probability the number of bolts above the average is linear in n, then why don't you try to use the standard induction proof from the bolts into bins paper by Eli Upfall, for example, the layered induction. You use the number of bolts above the average is linear, and you take it from there. Sounds very nice. Unfortunately, we still can have a load increase and decrease in that time interval. So meaning doing that induction is not very, very easy, because somehow the way that it's usually done, you have a maximum load of log n, and then you basically, you say that over time, you reach more and more the standard distribution if the maximum load is log n. So the distribution, how it looks, is very, very well known, and you kind of show that over time it comes closer and closer to that standard distribution that you have in these bolts into bins games. Unfortunately, a layered induction with like that, with the increasing or decreasing average, is very, very tough. So we did something completely different here. So what we did in that, we basically used the recovery property of bolts into bins games. So the recovery property, you find it in several papers, but for example, Arthur Schumer had a very nice result years ago where he looked at bolts into bins process with insertion and deletions, and he basically showed that the process recovers very quickly. So meaning if you give me an arbitrary distribution and you look at the difference between the minimum and the maximum number of bolts in a time which is polynomial to z and n, the system recovers. And he shows that the system recovers to its steady state distribution. Unfortunately, and that's what he says in the paper, we don't know how that steady state distribution looks like after his paper. He only says the steady state distribution we reach, but I don't tell you how it looks like. So what we now did is, and another thing is, our protocol, our process does not have a stationary distribution. So he basically looked at the system. You have m bolts in the, and then you insert, delete, and then you have, of course, a fixed number of bolts in the system, nice steady state distribution. We don't have that. Since our load is going up and down, there is no steady state distribution. But what we've basically shown instead is, so first of all, we showed via a layered induction that if you start in a completely balanced system for a polynomial number of times, the maximum load is log n. And that kind of made our layered induction much, much easier, because we say we are perfectly balanced now. And that then we were kind of able to show that for a polynomial number of time steps via layered induction, the maximum load is log n. So next step, what we basically did is we used couplings. we basically say that if you give me two systems, well, one of them starts at time t completely balanced, and the other one starts at time t with a maximum discrepancy of log n. We know that at every point of time with high probability, the maximum discrepancy is log n. So if you start with two systems like that, and you observe them for a polynomial number of time steps, they will end up in the same distribution. So meaning, what we have shown is, via layered induction, that for a long time, let's say n to the power of 5, the system load is bounded by log, the discrepancy. And let's say n to the power of 4 times the two systems need to reach the same distribution. That kind of shows something about, well, it's not a steady state distribution, but that is then sufficient to show that at an arbitrary point of time, the discrepancy is log plus a constant. So that is basically the proof idea. Yeah, I think the hardest part is a little bit well, that wasn't very hard, but one has to adopt a couple of results for Markov chain couplings, because usually one couples Markov chains in a steady state was different, with a Markov chain not in the steady state. In our case, both are not in a steady state, but that's not a big deal. I think you can couple arbitrary Markov chains with each other. And the most not so nice part is the layered induction, because making the layered induction with the average going slightly up and sometimes maybe a little bit down, it's not a very nice business, but that I would say are basically that was the hardest part of our analysis. So since it was a very short talk, I didn't prepare a slide with conclusions. So, but let me know if you have questions.
Questions?
So greedy 2 is still the best strategy to do in your setting?
I think it's a very good strategy, yes. I think it's able to recover very, very fast. I mean, you can do greedy D. And also, if you compare it to, I mean, what we've shown, it's a very good strategy for random insertions and deletions. It's not a good strategy if you have an adversary who determines when to insert and when to delete, because in their lower bounds they kind of play funny games. I mean, they manage to create a bin that has a relatively low load, and then you know that during a certain time period there will be much more balls being directed to exactly that bin. And that's I kind of used later on to create a bin with a very high load. So if you can play funny games like that, then and you use the knowledge that certain balls are allocated with a higher probability to certain bins, then that doesn't work very well. But if everything is completely random, then I think it's fine. And of course, you also have much higher problems if you look at the other model with reinsertions. I'm not sure if I want to analyze that, to be honest.
Maybe you just partially analyze this, but if you have adversarial deletions and you want to hurt the algorithm, it's complicated. How to use adversarial deletions to hurt the algorithm isn't simple.
Well,
I mean, you said play these funny games and you described something that was a little complicated.
It wouldn't necessarily call it complicated, but it is possible. But we kind of thought that is very unlikely to happen. I mean, that is not a typical sequence. So we decided basically to have a look what happens if you don't have that bad case, if you have kind of more averaged out. And I think you can also come up with nice adversaries that might not be able to hurt the system as much.
All right, let's thank the speaker.